Good morning. Welcome to Calculus BC. Now, today's not quite as rushed as it has been the last 2 days, so it gives me an opportunity to help us get straight down on the homework. I do now, just like 2 minutes ago, I put up the online submission button for the homework that's due today, 1.2. But since I got that up late, I'm going to give you until 3 o'clock to get it in today. Now, just a couple of words about the pace of the course so far and the homework. The pacing. This first unit goes way faster. I mean, you feel like you're holding on for dear life, or a lot of students do, holding on for dear life during the first unit. That's because, in fact, actually, just hold on for a second and don't even submit the homework yet, because there's something I want to ask you to annotate on the homework. So for now, just hold on 1 second. And if you did submit it already, you can resubmit up until 3 p.m. today. But you need to hear this about the pacing. Unit 1 has a lot of review of stuff we did in pre-calculus. Solving trig equations or learning a new way, a muck diagram-based way to solve trig equations. That's like, quickly reviewing things that is very different than teaching new material. Also, limits are things that you spent a fair bit of time already studying back in pre-calculus, which is why I am going hyperspeed. Reference to chapel today. We're going into hyperspeed on this part. So please don't be alarmed by that. Unit 1 goes super fast. Once we hit the beginning of Unit 2, then things are going to settle down to the standard pace that you're probably accustomed to back from pre-calculus pre-calc advanced, which was things were taught and you had time to learn them. So I'm not in teaching new material mode right now. I'm in quickly reviewing large amounts of material. So in case that was alarming to you, just want to let you know, it is unique to Unit 1. Also, for the homework, here's what I'd like you to do. Before you turn in the homework, I'd like you on each problem to compare your work to the work on the solution sheet, and then on your work, I want you to give yourself either a 2, a 1, or a 0 next to every problem. You just write 2, 1, or 0. So what does that mean? A 2, if you put a 2 next to your problem, that means that you had the answer and it was accurate before you even looked at the solutions. A 1, if you put a 1 next to it, that means you didn't really have the answer that was on the solutions, but you understand it now. Now that you've compared your work to the solutions, you fixed it up and you understand it. So no need for a question. A 0, if you put a 0 there, that means I do not understand this problem. Even after looking at the solutions, I do not know what's going on. So on each problem, I'm going to ask you to write either 2, 1, or 0. And then up at the top, I'd like you to summarize it for me. At the top, I'd like you to write a score out of 100, not one that goes in the grade book, because what goes in the grade book is a score out of 10. If you attempted all the problems, even if you don't understand all of them, even if they're all zeros, if you attempted them all, then your homework is an effort grade, not an accuracy grade, and you give yourself a 10 out of 10. The score out of 100 is an indication to me of how many questions there are. Like, for example, if your scores, and I'm just gonna write this on the sideboard, so we'll let Mandy see what's on the sideboard. Suppose you went through and you had 2, 2, 2, 1, 0, 2, 1, 1, 1, 2. Suppose these are your annotations on the 210 system. So this is obviously not always going to be out of 100. But what I want you to do is anything less than 2, subtract from 100. It's like, oh, you lost a point here. You lost 2 points there. So 1, 2, 3, 4, 5, 6. So we could say that you lost 6 points. So when you lose 6 points to 94 out of 100, that doesn't go in the grade book. That's just a signal to me so that when I look at your homework, it's like, oh, there were like 6 issues. What were they? Oh, there was a 0 in there. So I'm going to have to make sure that during the Q&A session, we handle the question that this student put a 0 on. So that's all. So please put 2 scores up on top. Something out of 100. Maybe it'll be like, turning the camera back here. Maybe something like a 94 out of 100 or 100 out of 100. I mean, obviously they can't get down to 0 out of 100 unless there were 50 questions on the homework and it were all zeros, then you could have a 0 out of 100. But you know, this is just an indicator to me of what's going on. This is what I will probably put in the grade book unless I see overwhelming evidence. I mean, if you gave yourself a 10 out of 10 and only attempted one of the problems, sorry, I can't really give you the 10 out of 10. You have to attempt all the problems in order to get full credit on the homework. So that's the 210 system. Do you have any questions on the 210 system for annotating your homework before you turn it in at 3 o'clock today? It'll ordinarily be turned in before the beginning of class, but this time it's 3 o'clock. Okay, so I discussed pacing with you and homework annotations. Now let's switch gears to actually taking concept questions on the homework that were not answered by the solutions. And by the way, how many of you had one or more of your homework questions answered by comparing your work to those on the solutions? Is there anyone who actually had questions answered? Okay, that's great. Lots of hands are up. That's what I'm hoping for. I'm hoping most of your questions get answered. Okay, what would you like to ask me about? Anything that's still confusing to you on any of the homework problems? Now's your chance. We don't want anyone to be left behind. We want everyone to stay on the AP Calculus BC bus. We don't want anyone falling off the bus. We're going to keep you here, Dave. Yes, Linda, go ahead.
So you want us to write out this statement, right?
Yeah, the statements, like for example, on number 29. It's not enough just to write the limit is 1/2. I want you to say that the limit is 1/2 and the graph is continuous at the point 1, 1/2. Yeah, that was for all of the page 71 problems that I wanted you to write the statements. Are there any other questions on the homework that's due today?
Mr. Wright.
Yes.
There was this one where we had to do like the muck diagram.
Yeah.
And it was titled like TE2.
Trig equation number 2.
Yeah. And
Cosine x equals radical 2/2. Yeah.
And I think the answer might be wrong.
Oh, yeah, it is. Wow.
Okay.
Wow, I'm glad you noticed that. Because it's not pi over 3, it should be pi over 4. So I'm going to change that on the solutions right now. In fact, you know what? Let me. Ooh, I'm glad you noticed that. So I'm going to close this up. Do you want to save? No. And I'm going to open it up and look only at that one. So, Madison, thank you. Yeah, I always want to get my solution sheets accurate, and sometimes, I wish I could give you extra credit for noticing that. Back in the public schools where I taught, I gave students extra credit for finding mistakes on the solutions. But here at Wheaton Academy, we don't do extra credit. Sorry to break it to you, but that's just not an option. So it's going to be pi over 4 plus 2 pi k and 7 pi over 4 plus 2 pi k. So that's going to look a lot more like this. Pi over 4 plus 2 pi k. And 7 pi over 4 plus 2 pi k for all k that are elements of the set of integers. We're going to save that. And then I'm going to print it to replace the previous one. Okay, are there any other questions on the homework? Things that are confusing? PDF, all pages. Okay. I did discover, I made a discovery, and that is that I had actually, two years ago, last time I taught this course was 2 years ago. 2 years ago, I actually did make a PDF of all of the Unit 1 notes in just one document. So it's now up there. Those of you who are PDF note takers, you can now go. And the very first PDF in the left-hand corner of topics, topic 1, topics Unit 1. Is all of the notes. Now, of course, that includes notes you've already taken, so I don't know how you want to organize your PDFs on that. But just so you know, all the rest of the notes are right there. Those of you who are doing paper notes, got them right here. So anyone who wants paper notes for today's lesson, there they are. Come grab them. So. Okay, now, the homework that's due tomorrow is homework 1.3. 1.3 is, this is Friday. Okay, so due Monday. Due Monday, next class day, at the beginning of class, is homework 1.3. And let me see if that makes sense. Yeah, because we had summer packet 1.2. So 1.3, homework 1.3 is due on Monday. And today's lesson is focused on continuity, which is what you'll be encountering in homework 1.3. In fact, one of the questions in homework 1.3 is to find a value of a that makes this piecewise function continuous. And so continuity definitely shows up. There is some review of limits in there. But and there are also part of the homework. So some quick sketches. Aha! Wow! I'm glad I saw that. Okay, there is one other detail I want to talk about in terms of things that I hoped you would learn from pre-calculus. And I'm just going to pull it in here. I put it in topics, and you don't have to look at it now, but it is up here. Under general resources, I put the 50 quick sketch equations. 50 quick sketch equations. These are 50 pictures that I would hope you would have with you from pre-calculus. Now, there's some good news here, and that is that the semis aren't actually used in calculus. So it's actually significantly less than 50, but these are the equations of them. I'll post the pictures later, but I want you to be aware of these 50 functions because students who do well in calculus, I do want to emphasize, this course is tried and tested and it helps students do really well on the AP test, really well. So part of that is having the right pictures in your mind. And for the sake of people at home on the camera, I mean, look at what, I'm just gonna switch to the board again. Look at what it is we're expecting. We're expecting that if you see these functions that you would be able to do a quick sketch graph of all of them. Like when you see y equals x, we expect you to say, oh yeah, it's this. It's a line with the slope of 1. When you see y equals x squared, that's quick sketch number 2. We expect you to say, okay, no big deal. We don't have to point plot. We know the shape of the graph. We expect you to know the shapes of all of those. Square root of x, x cubed. Those are quick sketches. If you don't know what they are, look at them on your calculator, cube root. Now, here's the ones you don't really need. The semis, we're not going to make a big deal of those. They're not going to show up on the AP test. Sometimes we'll look at them and they're not that tough. I mean, ellipse, yes, but not the semi-ellipses, the upper, lower, left and right semi-ellipse. So these 4 semicircles, don't stress out about those. The semi-ellipses, the semi-x hyperbolas, and the semi-y hyperbolas. However, it used to be 48 quick sketches. Now it's 50. So it's these last 3 that you may not be familiar with. So I want to look at those just right now. I want you to be aware of these last 3 because these are actually pretty important. I'm going to be referring to these as quick sketches 48, 49, and 50. So would you please, those of you taking notes on your Surface, would you please open up a blank document or maybe just add a blank PDF to what you've downloaded? The graph of sine x over x, think of this as the graph of sine x. But it has a variable amplitude. As x increases, the amplitude shrinks down to 0. That's what sine x over x does. So, now the truth is, there's a problem at 0 because sine of 0 is 0 and you can't divide by 0. So, sine x and x, those are 2 of the 50 quick sketches. If you were to look at sine x and x separately, they are both parent graphs. Sketches. The sine x graph, as you know, student stylus, here's the teacher's, with the student palette, here's teacher palette, there's a teacher stylus and a student stylus, which always goes with the student palette. Teacher stylus goes with the teacher palette. Sometimes you'll be up here, you'll get to use the student stylus with the student palette. So what's sine x? Sine x, you know what that graph looks like. It's one of the 50 quick sketches. Which one is it? Sine x is quick sketch number 33. Then quick sketch number 1 is y equals x. So when you divide that, what's going on here? We're taking the y coordinate to the sine graph divided by the y coordinate of y equals x. And if you superimpose them, it's like, wow, they get pretty close to the same graph. Locally, x and sine x are almost like, they're right on top of each other. And so sine x and x, as x approaches 0 from the right and from the left, it's like taking a number divided by itself, or at least pretty close. That's why the graph of sine x over x, which is quick sketch 48, has a hole at 0, 1, and it has an amplitude that shrinks down to 0. If you ever thought that graphs are not allowed to cross the horizontal asymptote, hello, here's a graph that crosses the horizontal asymptote an infinite number of times. And then it goes the other way too. Notice the amplitude is shrinking down to 0. That is the graph of sine x over x. It's quick sketch number 48. We expect you to know it. So that if anyone asks you to find a limit of this function, like what's the limit as x approaches 0 from the right of sine x over x? If you know the quick sketch, then you can get that limit in your head. In fact, I'm going to say the word pause in a few seconds. I'd like you to think about it. When I say the word class, I'd like all of you to say what the limit as x approaches 0 from the right of sine x over x is. So let's try. What is the limit as x approaches 0 from the right of sine x over x? Pause. Class? 1 is correct. If someone asks you to state the graphical significance of that, you would say, the limit is 1 and the graph has a hole at 0, 1. The limit is the y coordinate of the hole. There's a connection between the limit of the graph. If I said, what is the limit as x approaches infinity of sine x over x? Pause. I just didn't say it. What is it? Class? 0. Limits are output values. They're y values, and the y values are getting closer and closer to 0 is correct. If you know quick sketches, and there's a lot of calculus you can do just by looking at the picture in your head and writing down the answer. No algebra, no numbers, just pictures. It's putting the G in vegan tomorrow. Verbal, graphical, algebraic, numeric. For those of you who have a tendency to keep words and pictures at arm's length whenever you walk through a math room door, is there anyone willing to admit that that's your tendency, to keep words and pictures at arm's length? So, yes. You're all word and picture people? No? Okay. Are you willing to admit it in public? Yeah. Okay. Then the 50 quick sketches are the antidote for you. They're the pathway. The beginning of the path. It's a long path. It's a pathway to a 5. AP test. No, all 50 of these. I'll post the actual graphs for the 50 parent graphs. If you know the parent graphs, then you can usually get to their children. Their linear transformations of parent graphs are, we refer to them as children. Mathematicians call them linear transformations. So, okay, so that's important. Next one, absolute value of x over x. Absolute value of x over x. I mean, for positive x's, that's just number over itself, 1. So, can't divide by 0. So, next, there's 2 branches. There's a jump from 0, 1. When you're taking a negative number like -5, absolute value of -5 is 5, over -5 is -1. So those are all -1, -6, 6 over -6, 7 over -7. So this is the graph. It's a 2-branch graph, piecewise function, essentially. It could be written as a piecewise function. And so now if someone asks you, what's the limit as x approaches negative infinity of the absolute value of x over x? You can say, oh, it's -1. What's the limit as x approaches 0 of absolute value of x over x? 0 from the left is -1, 0 from the right is 1, so the answer would be, does not exist. The limit does not exist, and the graph has a jump from 0 -1 to 0 +1. So that's quick sketch 49. Quick sketch number 50. Yes, truth be told, didn't quick sketch 50, did you encounter that in homework? Is that like, oh, you've never seen this before, but hey, It's the sort of thing that you should know about, I think. Oh, it's 1.2. That's not till 10. Let me see, 1.3. I'm gonna look at 1.2 again. This was 1.2, page 1. Yep, there it is. Okay. It's like, I guess honestly, I'm a little bit surprised that you didn't ask. Ideally, I would have told you about quick sketches 48, 40 on this, quick sketch 50. You would have been way better prepared for this problem when you came to it on the homework last night. If you had known that the graph of sin x over x looks like your graph of this, because then you would have seen, oh, why is that limit 1? Oh, well, it's just quick sketch 48. I see the picture. Now, quick sketch number 50 is 1 minus cosine x over x, which it's a thing that shows up. It shows up pretty often, and so it's worth it to know the quick sketch of 1 minus cosine x over x. I actually typed it into Wolfram Alpha, and I just typed it in and he showed me the graph. But I want you to know it so that whenever you have to find the limit as x approaches 0 or any other part of 1 minus cosine x over x, you'll have an idea of what it is. So back to, where were we? It was 1.3, I think. So just so you know, you can type it into your calculator if you ever forget it. But there is a hole at 0, because you can't divide it by 0, but it's like, here's the right half of it, and here's the left half. It's like it's bouncing off the x-axis. It gets closer and closer to 0. So there it is. Those are 3 quick sketches that you probably didn't spend a lot of time with back in pre-calculus accelerated or pre-calculus advanced. Am I right? These were like not a big deal back then. Okay, so they are a big deal in calculus. So know those 3. Okay, next. There is a loose end from the beginning of the 10 connections handout that I just kind of skipped over, and it's a vocabulary issue. It's a difference between removable and non-removable discontinuities. Keep in mind that discontinuities you probably learned in pre-calculus. There's 3 types. The discontinuities consist of holes, jumps, and vertical asymptotes. Those are the 3 types of continuities, of discontinuities in mathematics. And the only thing, we don't have time to go through this whole thing, but this is all about saying, guess what? There's a vocabulary issue here, and that is there's a technical name for a hole. A hole in mathematics is called a removable point of discontinuity. Why? Well, if you read this definition, you will learn, I'm just going to tell you, because we don't have time to read it, but you would learn that if a discontinuity can be removed by simply either defining one output, like let's just say that f of c is 8, that would remove the problem. No more holes. Why are holes a problem? Well, suppose you're walking along this road, you encounter this hole. You might be going like this. You're walking along, you fall through the hole. No one wants this. No one wants to unexpectedly fall through the roadway. So if you can fix the hole in the road by just saying, either let's redefine it, there is no hope there. There's no way you can fix that hole if the only tools you have access to are either defining a function output or redefining a function output. Like right now, f of c is -7. We can that's removable. We can say, let's change f of c is -7 to f of c equals what? To remove to 8. If just change f of c equals -7 to f of c equals 8, that removes the discontinuity. So it's removable. Holes are removable points of discontinuity. The other ones are not. Jumps are non-removable. Vertical asymptotes are non-removable. So that's a vocabulary issue that we kind of skipped over, but you need to know that. So jumps, vertical asymptotes are non-removable. Any questions on the vocabulary issue of categorizing all discontinuities as either removable or non-removable? Okay, next, I'd like you to find in your notes the part that, we'll do that Monday. Continuity. Let's go to the continuity part, which is very likely the 4th page of the massive handout that has everything combined. Okay, here we go. Continuity. What is continuity? Continuity at a point. And put it all together, put all the points together, you can have continuity on an interval. Let's discuss both. It's probably a review for you. My guess is Mr. Polinsky went over this. Theorem on continuity at a point compared to theorem on limit at a point. Okay, so when it comes to limits, a limit at a point, how do you define that? Would you please call this the point A, comma, capital L? And two numbers have to equal each other in order to say that the limit exists at the point. If the limit as x approaches a from the left of f of x is equal to this other number, a second number, which is the limit as x approaches a from the right of f of x. And then parenthetically, if both of those happen to be equal to capital L, a real number, and it's not a third number, but if the left-hand limit equals the right-hand limit, and by the way, both of those are a real number, then we'll call that number L. So if the left-hand limit is L and the right-hand limit is L, then we can conclude, if those two numbers are equal, then we can conclude that the limit as x approaches a of f of x equals L. Okay, it's not continuous, but at least the limit exists. We have a discontinuity, there's a hole, even though there's a hole, even though we have a removable point of discontinuity, we can still say that the limit exists at x equals a. So if two numbers are equal, the limit exists. Now, continuity at a point, what's the definition of continuity at a point? Well, here we go. Continuity at a point. Questions on limit at a point? The green stuff, what is the green stuff? It's a parenthetical statement. So it's like, oh, by the way, if, it's not a smiley face, it's a parenthetical statement. So if, by the way, if both of these numbers are equal to a real number L, it can't be like find I, where I is the square root of -1. This is real valued calculus. You can take a course called complex calculus of non-real or complex numbers. But that's not this course. There's no I equals the square root of -1 in this course. Okay? All right. So now, continuity at a point. To establish continuity at a comma L, not just two, but three numbers have to all be equal to L, a real number. So if three numbers, the first one is the limit as x approaches a from the left of f of x, if that is equal to the limit as x approaches a from the right of f of x. And again, one of these videos are going to tend to talk about, I hope that doesn't alarm you, but I want to make sure that Maddie can hear me. And if that's equal to a third number, does anyone know what that third number would have to be in order to say?
F of A.
If they happen to be the same as the output when the input is A. If the output when the input is A is equal to these other two numbers, which, by the way, parenthetically, if all three of those numbers are equal to what we call L, which has to be a real number, then we can say that F is continuous everywhere? No, just at the point x equals A. F is continuous at x equals A. So if you want to support the conclusion that a function is continuous at a point, also there is for the interval, if f is continuous for all x that are elements of the set, parentheses a comma b, for all values of x on the interval a to b, then we say that f is continuous on the open interval a comma b. So for every value of x, it could be b to c, so we have continuity on an open interval. Okay, now there are three ways to justify a conclusion of discontinuity, because sometimes you'll be asked, based on the definition of continuity, justify that this function has a discontinuity at x equals 7. Or in other words, you're going to have to identify the part of this statement that broke down. And you need to understand that there are 6 ways in principle for it to fail. You need to get all 6 of them. 1 is that these two limits are not equal. 2, the left-hand limit does not equal f of a. 3, the right-hand limit does not equal f of a. Those are 3 ways it can break down. But there's 3 more. The 4th way is that the left-hand limit does not exist. The 5th possible breakdown is that the right-hand limit does not exist. And the 6th and final way for this to fail is if f of a is undefined. You say limits either exist or do not exist. Function values are either defined or undefined. So those are the 6 ways. And in any particular problem, there'll be many options, but there will never be more than 3 of those 6 in any particular problem. Let's practice that. On the next page, let's practice identifying all the different ways we could justify that this function is discontinuous at 5. And I'd like you to just try your hand at just counting. And I did kind of give away a big thing here. It'll never be, in any particular problem, there's never more than 3 correct ways to justify a discontinuity. But see if you can, so it'll be either 0, 1, 2, or 3. Go ahead and talk with someone nearby. Paul, I'm hoping there's someone you can talk with, or perhaps I'll come over there and you can tell me. But I'd like you to count. How many ways does the definition of continuity break down on this problem? Tell someone close by. So how many ways do you think
No one so far. Because if it doesn't exist, it limits your vote. There's more than one.
there's more than one? Okay, so please tell me how many ways. A total of 0 ways and 2. Okay, I'd like you to hold up either a fist, 1, 2, or 3 to indicate, like currently, you may not have had enough time to fully analyze this in your mind, but where are you leaning right now? Is there a total of 0 ways to justify the discontinuity? 1, 2, or 3? Go ahead, in 4 seconds, display your response for 3, 2, 3. I see 1 and 2. I see 1, 2, and 3. Okay, so let's find out. So I see 3. Okay, so a lot of people are saying 3. Class, let's find out how many there really are. How many ways are there to fill in this blank? F is discontinuous. Let's write this down. At x equals 5 because blank. So I basically asked, so a lot of you, those of you who want like this, you think there's 3 ways to fill in the blank. You only need 1 to justify it, but I want to know how many options you think you have. Okay, so what's one that you think that you can use? Because, what? Linda, do you have one? I mean, you said you have 3 of them, Joan. Could you give me one of your 3?
F of 5 is undefined.
Okay, so one way is to say f of 5 is undefined. Okay, that is correct. That will justify the claim of discontinuity. Now, who thinks they've got another one that we could have used instead of this one? Yes, go ahead.
Creating the limit as x approaches 5 from the left does not equal the f of 5.
Okay, now that's probably I see why a lot of you said 3. It's actually only 1. And the reason that we can't use that one, and here's why. Here's why. If you try to fill in this blank, and a lot of you said 3, a lot of you thought that this was going to be okay. But if you tried to say the limit as x approaches 5 from the left of f of x does not equal f of 5, that's not acceptable, because it's a misuse of the does not equal to symbol. I don't know if you're aware of this, but the does not equal to symbol is a binomial complex number truth tester. binomial needs two complex numbers. Now, in this course, we don't deal with non-real numbers, so the only complex numbers we deal with are real numbers. So we need two real numbers. Now, it turns out that this is a real number. This is the number 9. 9 does not equal, the problem is f of 5 is undefined. So if you want to go around saying 9 does not equal undefined, that's like saying 8 does not equal elephants. Or they're not comparable. An elephant is not a real number. Undefined is not a real number. So if you have two real numbers, then you can use the binomial complex number operators like equals and respond with either true or false. Does not equal to, greater than or equal to, less than or equal to. You need numbers on both sides of those symbols in order to have intelligible statements, in order for them to be legitimate questions. So this is difficult for students to grasp, so every year I try to take a little more time with it in the midst of an otherwise very speedy review of pre-calc, but we just can't use that one. Can't use it. There's only one justification. Here, this is fun. Let's do some more. Try number 2. Count the number of ways to justify the claim of discontinuity. F is discontinuous. And x equals 5 because blank. Tell someone how many ways there are to justify the claim of discontinuity. Going to pause the camera while you're counting. So here we go. Is it 1, 2, or 3? Class, how many ways are there to justify the claim of discontinuity? I'm seeing a lot of people hold up 2 fingers. Now, to me that sounds pretty reasonable because sure enough, the left-hand limit does not equal the right-hand limit. That's one way to say it. So one way, you only need one, but one of the options, if I'm grading this, I would have to give full credit to someone who says the limit as x approaches 5 from the left of f of x does not equal the limit as x approaches 5 from the right of f of x. Okay, that'll do it. What's the other one? And you're right, there is another one. Can someone tell me what the other justification is? Raise your hand if you're reasonably sure to articulate that, or if you're reasonably sure you can articulate that out loud. Paul, you want to give it a go?
The limit as x approaches 5 from the left does not equal f of 5.
Yeah, the right-hand limit equals f of 5, but the limit as x approaches 5 from the left of f of x does not equal f of 5. Well done! There they are. Any questions on that? Now, we aren't going to go through all the details, but let's just count this one up here. So, did you just go back down? Oh yeah, you want more time, right? Yeah, so, or the limit as x approaches 5 from the left of f of x does not equal f of 5. Okay, so there they are. Sure. Now, how many other up here? I'll just count. I see the left-hand limit does not exist. The right-hand limit does not exist because it goes to infinity. Is there a third? Or is it only 2? F of 3 is undefined is correct. Now, by the way, if I had a point, this is very rare, but sometimes you see a point on a vertical asymptote. If f of 3 had been 9, which is possible, then there'd be only 2 ways to justify it. Because f of 3 is defined, so you can no longer say f of 3 is undefined. Likewise, over here, if the point 5, 12 had been defined, then f of 5 is undefined would no longer be a legitimate way. It would no longer be the one and only way. Then there would have been 2 ways to justify it. We would have been able to say the left-hand limit, 9, does not equal f of 5, which is 12. And we would have been able to say that the right-hand limit, 9, does not equal f of 5, which is 12. So if this had been there, there would have been 2 ways to justify the claim of discontinuity. Does that make sense? So we kind of got we squeezed some extra learning out of those problems. Let's go to our last example for today. We've got 5 minutes to take you through this last example. And here it is. You have to do one like this on the homework. It says, find values of A and B that make it continuous. So it's like we have 2 branches of a road, and it looks like something's wrong. There's a discontinuity unless we pick the right values for A and B. So in order to pull these off, I am going to require, so that you really deepen your understanding of the definition of continuity, I'm going to ask that you take a 3-stage approach to these. even though you could do it using Algebra 1. You don't need calculus for this, but we're going to do an exercise to deepen your calculus. Stage 1 is going to be a system. This will be required on the homework due Monday. A system with, not of, but a system with limits and f's. The second phase, it's an exercise, will be a system with limits but no f's. A system with limits and no f's. And phase 3 will be a system with neither limits nor f's. Here's what that looks like. Class, what's going on is that when x is less than 2, I mean, basically, here's x equals 2. Less than 2, we have one branch, it's like a parabola. Then to the right of 2, we have a line, an open circle here. And the branches don't meet, the cars are falling off. It's like it's not continuous, it's a jump discontinuity, unless we pick the right values of a and b. So system with limits and f's would look like this, exactly like this. In order to solve for a and b, I need the limit as x approaches 2 from the left of f of x to equal f of 2. And I also need the limit as x approaches 2 from the right of f of x to equal f of 2. It's a system of 2 equations that contains limits and f's. Okay? That's phase 1. Phase 2, I'm going to erase this, so you already wrote it down, so I don't need it here anymore. Phase 2 is where we get rid of the f's. Okay? So, limits but no f's. So it's a limit as x approaches 2 from the left. Which version of f of x do I use here? Well, approaching from the left, that's less than 2. So I replace this f with ax squared plus bx. And f of 2 is 6, so equals 6. Okay? So would you please do the same here? Would you get the f's out of this second equation? Limits and no f's. Okay, so replace, there's 4 f's. This third f is replaced with 1/2 ax minus b. That one's, okay, so that's phase 2. Phase 2 is done. Phase 3 is where I have neither limits nor f's. So to find the limit as x approaches 2 from the right, it's really not too bad. Just replace all the x's with the number 2. So you get the third system is 4a plus 2b equals 6. And the second equation in the system, put a 2 in for x, half of 2 is 1, so it's a minus b equals 6. Okay, so that's phase 3. So now it's an Algebra 1 problem. We solve the system. And if you solve the Algebra 1 problem, you get an answer for a and b. So I want you to use the definition of continuity in order to find values of a and b that cause the piecewise function to be continuous. And really, right here is where we're using the definition of continuity. We know, I mean, I could have said the left-hand limit equals the right-hand limit. That was an option, right? But I wanted to pick it as streamlined as possible. So instead of left-hand limit equals right-hand limit, I said, oh, look, I'll say this equal to 6 and that equal to 6. So that's going to be required. It's going to be, there'll be one like this on the test. The test will be toward the end of next week, the Unit 1 test. And I have a review packet for that. It's called the problem set. I'm just going to hand it out. And this is one of the few things every unit is a paper submission. I want you to turn in the problem set on paper. I see if I can find it. Problem set, where'd you go? It's posted online, but I'm going to give you a paper copy of it because there's some things I just want to look at. So I'll give this to you on your way out of the room. But the homework for Monday, oh, here, found it.
What about A?
No,
Ryan, can you please stop by the nurse's office? Thank you.
So, this has the answers on the back, but you have to provide the solutions on paper. Go take one of these. That's due a week from today, so you have a week to do the problem set.
And you want us to do it on a separate piece of paper?
It's gotta be on a separate sheet of paper.
Oh.
Okay, so that's one paper assignment every unit.
So we turn it in paper?
You'll turn it in paper a week from today.
Okay.
So 1 week, maybe
When's
do,
the test?
like, it'll be next Friday.
Next
Test will be
Friday?
next Friday.